In this video, we'll be seeing how a closed loop buck converter basically works. So on the screen, I have a black box which depicts the behavior of a buck converter. And at the bottom, I have a black box which depicts the behavior of a control system, since this is closed loop operation. So the ultimate aim here for having a closed loop operation is the input which we are going to supply to the power circuit may not be a constant. If it is coming from a battery, the voltage depends upon the state of charge of the battery. Or if it is coming from a DC bus, it depends upon the transients happening in the DC bus. So I mean to say that the input voltage coming to this power circuit, power converter, is not a constant. So when you talk about a buck converter or a synchronous buck converter on a system level, this is how the input and output are related. So we have a duty ratio here, which is multiplied by this input voltage to give you the output voltage. Now assume that I have a specification such that I want to convert 24 volt into 12 volt. So the duty ratio here would be obviously 0.5. It will be my nominal duty ratio under ideal conditions. Under practical conditions, it will be slightly greater than 0.5 to compensate the voltage drop across the various parasitics inside that circuit. Right. Now, assume that this 24 volt, due to some reason, is increasing to 25 volt. Now, if this voltage is increasing, and if I am keeping this duty ratio fixed, then the output voltage will also increase. It will probably go to maybe 12.5. On the other hand, if the input voltage falls down below 24 volt, maybe to 23 volt, then the output voltage also falls down, maybe to 11.5 volt. This sort of change in the output voltage is not desired, because when we say DC-DC converters, we promise to deliver a fixed voltage at the output. Now, how to fix this? The fixing of this problem goes with a closed loop control. Assume that initially you are having a fixed input voltage which is at your desired level. For that level, you will get a desired output. If the input voltage increases, then you will have to decrease your duty ratio so as to obtain the constant output voltage. On the other hand, if your input voltage decreases, you will have to increase the duty ratio accordingly to get the desired output voltage. How does that work? It works as a simple mathematical equation. You have V0 equals D into V in. Your V0 is required to be constant. So a constant should be equal to D into V in. If my V in is increasing, then your duty ratio should decrease to maintain this constant. And if your V in is decreasing, then your duty ratio should increase to compensate this decrease in the input voltage to maintain your V0 constant. So what a control system essentially does is it takes the output voltage inside it, does some computation. At the end of the day, it gives you a duty ratio. And when I mean to say duty ratio for system level understanding, it's just a mere number. When I say duty ratio on the real world, it will be implemented as a PWM. And this will be your D. This upon your total, this will be your D. That is your on time of the switch divided by your total switching period. This will be your duty ratio. So this control system should be able to sense the output voltage and adjust the duty ratio or adjust the width of the PWM signal you are giving to the switch. This is the motive of having a control system, and this is the system level understanding of how a buck converter in closed loop system works. You can replace this buck converter by any DC-DC converter. Ultimately, this is the aim. Moving on, what we saw earlier is a system level representation of a closed loop converter. Now we are going to step into little bit more details, emphasizing on each component or emphasizing on is essential component inside uh, control system, which is shown in this diagram. So we will enter into this. You could see that here we have the entire buck converter. It could be a synchronous buck as well. Just replace the diode by a switch and operate it complementary to this high side switch. Now let us focus on the control part, which is starting from here, which is voltage measurement, and ends here, which is obviously a PWM, which is going to be given to a switch. So now we could focus on the functioning of this. First, we will measure or sense the output voltage in this section. So this will be our V0. We give it to a comparator, which will compare this V0 with the reference value. Assume that my converter specification is to convert 24 volt into 12 volt. So whatever voltage is measured here will come here. It will be compared with the reference value, and an error will be produced, which will be given to the controller. The controller will take the error inside and give you the duty ratio outside. I am stressing this because this is a very important point. You have to note that the output of the controller block will be duty ratio. We'll come back to the controller again to discuss that in detail. Now this duty ratio will be essentially a number which will vary between 0 and 1 in ideal conditions. Then we produce a sawtooth waveform which varies between 0 and 1, and we compare this duty ratio with the sawtooth waveform with another comparator, and then we produce the PWM here. This PWM will go and operate the switch. This is the overall explanation. And now let us go into a deeper explanation. Assume that my output voltage here at this point, it's not 12 volt. Let us assume that it is having a voltage of maybe assume that it has a voltage of maybe 11.8 volts. Now this 11.8 comes here. My reference will always be held strictly at 12, and the error of 0.2 volt. So how is the error calculated? Error is nothing but V reference minus V0. So the error will be 12 minus 11.8, which will give me 0.2. This error will be fed into this controller, and the controller will produce a duty ratio corresponding to this error. Now that duty ratio may be somewhere around 0.51. Now here this sawtooth will produce, let me open the graphical way for representing it better. Yeah. Now this sawtooth initially was varying between 0 and 1 like this. This is 0 and this level is 1. Now I am saying that this duty ratio is having a value of 0.51. So the duty ratio will cut this sawtooth somewhere near here. Now because of this, the comparator will do its action and it will produce a PWM according to this. Whenever the duty ratio is dominating, you will have a high pulse here, and whenever the sawtooth is dominating, you'll have a low pulse. Whenever the PWM is dominating high, whenever the sawtooth is dominating low, you will get a PWM like this. This PWM will be fed into the switch. Now, as I said, the duty ratio required is 0.5, but we have 0.51 now. Because of this 0.51, the output will not go and settle exactly at 12 volt. Rather, it will go and settle at some voltage slightly greater than 12. Let us not go into the exact mathematics. Since I am saying slightly greater than 12, let us assume some voltage of 12.05 maybe. Now, the error computed here will be negative. Why? Because this 12.05 will come here and this 11.8 is no longer 11.8, it is 12.05. And this 0.2 will change to minus 0.05. Now you have a negative error here. And because of this negative error, the duty ratio will fall down to maybe some value called 0.495. Now 0.495 will be lesser than the previous value here. It will be somewhere below this, and because of that your PWM will be slightly shorter, or the width of the pulse or the on time of the pulse will be slightly shorter than the previous case. Now because of this, the voltage will drop. So what I am trying to explain here is, you are giving input voltage. There is assume that there is a PWM already. Because of that PWM, we get output voltage. The control system will sense that output voltage, generate an error, give it to the controller. The controller will give the duty ratio, and the duty ratio will be compared to the sawtooth waveform, and then it will produce a PWM, and then it will reflect to the switch. Now this action will take place in a corrective manner so as to maintain the output voltage at 12 volt constant. This is how the components, the individual components of the control system are put together to form your overall closed loop system. Now, coming to the controller. When I say controller, in DC-DC converters, it could be a I controller or a PA controller or a PID controller. And it could be directly observed that the integral portion is common among all the three. Means that an integrator is compulsory. Why? Whenever you want to maintain the output of something as constant, there are two ways. Assume that I want 12 volt. I can maintain the output constant, but the constant output voltage could remain at 11.8 volt itself. It could be a constant 11.8. I do not want that. I want a constant of 12. Or on the other hand, it could be a constant of 12.2. Even my output is constant. It's not at constant 12. I require 12. So what I mean to say here is that controller action alone is not necessary. The steady state error should be 0 whenever you have applications like this. That is why we go for an integrator which is compulsory.